And we will conclude our session with a talk by Ruyi from Peking University. He will present his work on improving oracle-guided inductive synthesis by efficient question selection.
Thank you. So, will it work? Oh, sorry. Oh, great. So, hi everyone. My name is Ruyi and I come from Peking University. So it's my great honor here to present our recent work on accelerating program synthesis. And the title is Improving Oracle-Guided Inductive Synthesis by Efficient Question Selection. So as a start, let us introduce some necessary background on program synthesis. Program synthesis is a problem about automatically generated programs satisfying some user-provided specifications. And in this slide, for simple, I shall focus on a very popular framework named counterexample-guided inductive synthesis. In this framework, programs are synthesized by interacting between two key components. The first is an example-based synthesizer, and the second is a verifier. The verifier keeps the full specification of the target program, and in each iteration, the synthesizer just generates candidate programs, and this program will be verified by the verifier. If it is incorrect, such as this case, the verifier will select and generate a counterexample to let the synthesizer generate more accurate candidate programs. And if it gets in the correct program, then the synthesis will succeed, and this program will return. And in most cases, when we are talking about designing program synthesizers, the first thing we would like to do is to let our synthesizer as efficient as possible. So to improve the efficiency of program synthesis, there has been a huge number of research efforts in designing efficient program synthesizers. So I believe the names of such synthesizers can fulfill this slide, but I just can only list some of them. And however, there is another, not seems so important in previous studies. There is a component named the verifier. And in the synthesis procedure, this verifier just plays a very important role to select among different counterexamples. So here, a natural question here is that whether we can improve the efficiency of the whole synthesis procedure by selecting different counterexamples. Let us consider a very simple case where there are three different programs remaining, where the first program is what we want, and there are two different inputs that can form counterexamples. On the first input, two programs output the same, and the third are different. And on the second input, all the three programs are different from each other. Then, suppose now, if the verifier selects the first input as a counterexample, then some problem will happen. We can find that the synthesizer can still return the second program as a new incorrect candidate program. At this time, it will lead to another iteration and also another invocation of the synthesizer, leading to a great time cost. And in contrast, if the synthesizer can find the second input to form the counterexample, then the target program will become the only choice satisfying all examples, so that the synthesis result must be correct. So, therefore, we know that selecting different examples may result in different efficiency of program synthesis. And motivated by this point, in this paper, we aim to select examples that can reduce the number of iterations, which will in turn improve efficiency of program synthesis. And to start, the first question is that since we can only measure the number of iterations after the whole synthesis procedure finished, how can we know whether an input is good in some intermediate round? We have studied this problem in an existing study on interactive program synthesis. The basic idea is that a good input should lead to different outputs for different programs in the program space. In this way, we can distinguish correct programs from the others based on their output. As a result, a very useful strategy we denote as the mean pair strategy is we can use the number of pairs of programs that output the same to measure the effectiveness of an input. And what we need to do is to select the input that minimize this factor. Recall the previous example that we already know that the first input is not so good and the second input is better. Let us check what will the mean pair strategy say and compare among these two inputs. On the first input, there are 5 pairs of programs output the same, 4 output 0 and 1 output 1. And in contrast, for the second input, there are just 3 pairs of input output the same. there are just 3 pairs of programs output the same. So we can see that the min pair strategy just tells us the same conclusion about which one is better among these 2 inputs, quite smart. However, the problem is that even though this strategy seems quite effective, the problem is that the approach for interactive program synthesis cannot be applied to, for example, accelerate program synthesis. The problem is that in interactive program synthesis, there is a very long user response time because the user needs to think about what to do. So we can use this time to select the best input very carefully. But in the non-interactive setting, because our goal is just to accelerate program synthesis, therefore we must be careful that the time of selecting a better input should be small, and at least it should be smaller than time it saves. In other words, we need not only to select better inputs, but also need to ensure that only a small overhead is introduced. So, realizing this scalability challenge in this paper, we focus on reducing the overhead of selecting inputs, and meanwhile follows our previous study that use a min pair strategy to select examples. What is the main challenge? The main challenge here is that the min pair strategy is so complex that even calculating the objective value for a single input is time-consuming. That is, the number of pairs of programs that output the same. Let us recall the previous example again. We already know on this example there are 5 pairs of programs output the same. But how can we calculate this number of 5? First, we need to evaluate every program in the program space, and second, we need to compare all pairs to count up how many pairs has the same output. But the actual case is that the program space can be extremely large so that we can neither evaluate all programs nor compare all pairs. So how can we address this challenge? So the first thing is that we can use some domain knowledge. One very important domain knowledge about program synthesis is that in a program synthesis task, the space is usually specified by a very small and simple grammar. And also we can assume this grammar is finite because we can always cut off this program space with a large enough depth limit or size limit. So, utilizing this structure, we can calculate something very efficiently. That is, if we can calculate a value recursively along with the grammar, then the time complexity will be bounded by the size of the grammar, then it will be very efficient. So, now we have some way to efficiently calculate something, and our final goal is to calculate the objective value, that is the number of programs that output the same. So let's just have a try what will happen. To demonstrate this procedure, let us consider a very simple grammar. It just involves 2 non-terminals, and A expand to B plus B, and B expand to some terminals. And also let us consider a very simple input that X is assigned to 0 and Y is assigned to 2. The start case is the lower non-terminal B, which includes only terminating expansions. This case is straightforward because we can just enumerate all terminals and check whether the outputs are the same and just record the answer. And as a result, there are 3 such pairs that output the same. The most important case is that how to combine the recursive results on non-terminal B to the results on non-terminal A. To see this point, let us consider 2 arbitrary programs in the space of non-terminal A. There are 2 different cases. The first case is that the subprograms are very luckily output exactly the same. Then we know that their 4 output must be the same because X must produce the same output from same input. At this time, from the recursive result, we know that there are 9 pairs of such program pairs, so that this case contributes to 9 pairs to the result of non-terminal A. But some problems will occur about the second case, that is, the sub-results are not so exactly the same. At this time, we can find that the behavior actually depends on concrete sub-outputs, which is also dependent on the concrete behavior of the plus operator. We can list some examples that, for example, in some cases it outputs the same, and some cases it outputs differently. It totally depends on what the concrete result is. But please know that what we want to do is to calculate along with the grammar. And at this time, we don't know what the concrete output is, so our calculation simply fail here. Let me make a summary. What struck us is that the behavior of operator X, of operator plus, depends on the concrete sub-output. It is too complex. What can we do? Just throw away it and replace it with some simple thing. So let us estimate it using some very simple operator that when some different inputs are provided into it, it always has a fixed chance of 10% to return the same output. Then let us see what will happen. The first case is the same, so we can just move to the second case. Then at this time, we can say that each pair has exactly 10% chance to output the same. And we know there are, maybe it is not directly, but from the size of non-terminal A and the recursive results, we know that there are 72 pairs remaining that belongs to this case. And then it will contribute 7.2 pairs in expectation to the result of non-terminal A. In this way, we can push forward the calculation and thus calculate the number of program pairs that output the same in a very approximate way, but very efficient way. This is just our idea. We just estimate every operator using very simple random events to ensure that the objective value can be calculated efficiently. Our approach can be integrated into a verifier, and each time we want to calculate a counterexample, it will first generate a series of candidate inputs, and then train a model for each candidate input. The model includes parameters for estimating operators. For example, for the previous plus case, we have a parameter equals to 10%. And then the third step, we will calculate the approximate objective value for each input, which is equal to the expected number of program pairs that output the same. And at last, we just return the best. So that's totally our approach. And the next step is the evaluation. So our core idea is our final goal is to accelerate program synthesis. So the most important thing in our evaluation is to check whether this goal is realized. So we just consider 3 different common synthesis domains and several different synthesizers, and compare our approach with the default verifier on all these synthesizers and all corresponding domains. The result turns out that our approach can achieve speedups for all domains and all solvers. Note that this speedup is for free because from the very start to very end, we just treat the example-based synthesizer as a black box. So, at last, I would like to take some minutes to talk about something about our approximation. So, essentially, our key idea is to estimate the output distribution of a program space with some very, very simple random model. So it may seem very counterintuitive that why it works, because all of us know that the behavior of a specific program can be very complex. Our argument is that even though an individual program can be complex, the behavior of the whole program space can be easy and predictable. We can find many related concepts in other domains, such as in psychology, there is a concept named crowd effects. That is, if there are many people in a group sitting together, they tend to lose their individuality, and we can easily predict their behavior. So the program space is just something like a group of programs, and maybe when we want to estimate the overall distribution, it is not so important to care about the accuracy of some specific program. We can also make some simple demonstration. Let us consider a very simple grammar, just include some two inputs and 2 constants and some comma operators. And then let us consider a fixed input and a depth limit. We can plot the output distribution of these programs within the depths into a figure. And we can say if the depth is 0, we can clearly find something that belongs to the concrete behavior of constants and inputs. And as the depth grows to 1, we can also find something like the semantics of plus and semantics of minus. But the point is that when the program space becomes large enough, such as the depth grows to 5, then the distribution turns out to be quite simple. It's just something like a normal distribution. So, and approximate such a distribution will not be difficult. So that is my presentation, and I would like to stop with some simple conclusion. And in this paper, our goal is to accelerate program synthesis by selecting better examples with a very small overhead. To select better examples, we follow one of our previous studies that used mean pair strategy to select examples. And also to reduce the time cost, we estimated the behavior of operators to make everything can be calculated efficiently. This is some example of our approximation. And we implement our approach and evaluate it again on several different domains and with several different synthesizers, and the results show that we can indeed achieve some speed ups. Yeah. That's all. Thank you very much.
you for this very interesting presentation. Are there any questions? From your experience, does it depend on the type of operators that your language is supporting? Like, does the complexity of the base operators that you use for generating the programs, does it influence the quality of the counterexamples?
Yes, of course. The quality of examples will diverse between different domains, and it will just change. And then for example, on the domain of string, and the operator will be, and the input-output behavior will become much more complex. But meanwhile, at this time, if we can find a really good counterexample, we can exclude a very large number of candidate programs. So it just depends on some domain knowledge, and there will indeed some changes.
Okay, thank you. Last chance for question? If not, then let's thank our speaker again.